In this lecture, we are going to discuss some more examples over DFA, NFA, and then we see what is regular language. So, we take a question. Construct a DFA over summation equal to AB such that it will accept all strings with even number of A's and even number of B's. So, this is our question for which we are supposed to construct a DFA. Now, how can we proceed? First of all, we take some example string. For example, condition is even number of A's and even number of B's. So, A, B, B. In the string, number of A's, they are 2, number of B's, they are 2. They are even. So, it must be accepted. Similarly, A, B, in the string, number of A's, they are 2 times, number of B's, they are also 2. So, it should be accepted also. Similarly, A, B, B, A. In the string, number of A's 1, 2, 3 and 4. Number of A's there 4. Number of B's there also 4. So, it should be accepted also. Okay. Now, A, it should also be accepted. Why? Because number of A's there are 2, number of B's therefore both are even, so it should be accepted. So now we try to construct a DFA. But the most important thing we should notice here is null string. In null string, number of zeros is number of A's is 0 time, number of B's is 0 time, and 0 is even. So our DFA is going to accept null. Okay. So now we try to construct a DFA. We take Q0 as initial state. From this Q0, we take a transition as with labeled A to new state, that is Q1. From Q0 to another is we take this transition as with label B. Similarly, because number of A's must be even, we take another A's from Q1 to Q0 with A, from Q2 to Q0 with B. Now, transition edges from Q1 for alphabet B, they are missing. Similarly, transition edges from Q2 with symbol A, they are missing. So, we take another state, it is Q3. It should be labeled by B, again B. From Q2 to Q3, A, and from Q3 to Q2 via A. Now our DFA is complete. Now, which state should be taken, should be made our final state? So because our DFA is going to accept null also, we make our initial state a final state also. Okay. Now, we try some strings which we taken earlier. A. From Q0 to A, we move to Q1. From Q1 to A, again we are at Q0. From Q0 to B, we move to Q2. From Q2 to B, now we come to Q0. All the input symbols they are consumed, and we are at final state Q0. So this string is accepted. Similarly, this AB, it should be accepted also. So from Q0 to A, we come to Q1. From Q1 to B, we move to Q3. From Q3 to A, we move to Q2, and from Q2 to B, we move to Q0. All the input symbols they are consumed, and we are at final state Q0. So this string is also accepted. Similarly, null is also accepted because initial state is our final state. Okay, so this is our example DFA, which is going to accept all strings over A and B in which number of A's is even and also number of B's they're even. Now, the language which our DFA or NFA is going to accept, it got a special name, and that is called a regular language. So which language is said to be regular? If somebody says, what is a regular language? Then what it means actually is, for that regular language, we can construct a DFA, or we can construct a NFA, or we can write a regular expression for that language, or we can write a regular grammar. But grammar is not taken at this time, so I don't mention it. So if a language is regular, we can construct a DFA for that language, we can construct a NFA for that language, and we can write a regular expression for that language. Then only we can say the given language is regular. Okay. Now our question is, given L equal to a to the power n b to the power n such that n greater than equal to 0, I design a DFA for it. Okay, can a DFA be designed for this language a to the power n b to the power n? After few trials, we can notice that no DFA can be designed for this language. No DFA. In fact, no NFA also can be designed or constructed for this language. Similarly, we cannot even write a regular expression for that language. We cannot write or construct a regular expression for L given above. What it means actually? It means maybe the given language is not regular. Then only we cannot construct a DFA or NFA or regular expression for it. But how can we actually recognize the given language is regular or not? For that purpose, we got a lemma, and that is called pumping lemma. Which is our topic of discussion for the next lecture. In the next lecture, we see how pumping lemma for regular languages can be defined. Okay.